another coordinate in our life, just like space-time. But interesting thing is that we can move in the three space coordinates as we desire at our will, but we cannot move in time by our desire as we like. So we cannot go back in time, for example, or we cannot accelerate the progress of time in our life. Hmm. This is something that we don't have a control on. Although general theory of relativity, general relativity proclaims that it is possible to contract time, expand time as we change the speed. However, this is not the purpose of this talk here. You will find many philosophical treatises on time. People have been thinking about time from time immemorial. And there are hundreds of proverbs around time, built around time. गुजरा हुआ जमाना वापस नहीं आता, आगे का समय कौन जानता है. लोग तरह तरह की बातें करते हैं टाइम को लेकर के. So I will not go into the philosophical aspects of the time here, which is very interesting in itself. And that we can discuss some other time maybe. What we are going to do here is about the measurement of time, how we do carry out a precise measurement of time. That means what we want to know is how we measure the time interval that as the time passes, how precisely we can measure this time interval. As you will see, this is going to be very important. This is already very important in our lives, because most of the technological marvels that we use every day, that we unknowingly or knowingly, we depend on them every day. They depend on a very precise measurement of time. For example, if I ask you a simple question, how the world time is kept and synchronized around the globe, who keeps this time? So when we say that this is that the time over here, for example, is 3 o'clock, then we know that what this means, 3 o'clock past PM. So what does it mean? And it has some meaning in New Zealand, and it has another meaning in England or Russia. But we know that what exactly, how we can convert it to their time, and it will be exactly the same time. So the world time is kept by technological marvels in themselves. And these technological marvels, they are based on many scientific discoveries. And the precision with which is kept is very, astounding, as we will see. There are labs around the globe, and I think there are not more than 6 or 7 labs in the world, which are timekeepers of the world, and they keep the time of the world clock ticking, and they synchronize with each other continuously. And the time measurement that they use, that technology that they use nowadays, is known as optical atomic clocks. So generally, when we say clock, we mean something, in the old days, there used to be a clock in homes. Every home used to have one clock at least, which will make tick, 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 tick. And it is running, time is running out. And the precision of that clock was not very much actually. So in today's world, science and technology have become kind of entangled and intertwined. Mm. Scientific discoveries eventually lead to new technologies, sometimes in years, in decades, sometimes even it takes 50 years or 60 years for one of the scientific discoveries to give you fruitful technological gains. And then when new technological inventions are made, they lead to still newer scientific discoveries. So new scientific discoveries follow. So there is a chain. Hmm. We need science to make technological inventions. These inventions lead to new scientific discoveries, and they lead to new technological inventions, and so on. And this chain has been going on for last 300-400 years continuously when modern science started. So as we progress, we will see some glimpses of these statements in our in this talk also. This is a small book. I have this book in my library here. I am a physicist. This is the name of the book. The book is written by a Russian physicist, Kitai Gorosky. Kitai Gorosky was a very, very thorough physicist, and he wrote this book to explain what does it mean to be a physicist, why I am a physicist, how I became a physicist, and why I would like to continue the life of a physicist. It's a very well written book and very in simple language. And I found this book in my childhood when I was maybe in class 10th or 11th. I started my university course in 11th itself. So, and in those days, books were not very freely available. Nowadays, you can go and download reams and reams of material from internet, Google, and so on, and probably not read it. Reading of books has become very, very rare thing nowadays. Hardly, I haven't found any student reading a book, a serious book or anything, a complete book in itself. But books were very rare in my time. And any book that I can lay a hand upon, if I can buy it, I will buy it, or I will borrow it, and I will read it. And you have to read the books completely from page 1 to last page. And that is the reading of the book. Nowadays, you have got Kindle where you can have hundreds of books, but not many students read their books actually. So I will strongly advise the students to choose at least one book every month and read it completely. I used to read at least one book every week actually. And I will go for shopping for books every day almost because books were very expensive. So I will look for the cheap books. And Russian books were the best source because Russia, in those days, the Soviet Union, in their attempt to push the communist ideology, they used to push their literature at very, very cheap rates. So this book I found in one of such shops, and it influenced me quite a bit. For example, Kitai Gorosky lists the attributes, most valuable attributes that a student must have. He says, you must have an excellent memory to absorb. So if you can remember things nice very well, that means your half of the job is done. So excellent memory to have job. Memory should be very good. Then there should be a tenacity to walk the path alone. That means you must have that capacity, that strength to walk alone and not worry about others, what they are doing or what they are thinking about you. Then third thing is stubbornness to achieve the goal. You must be very, very determined that this is the goal that I have to achieve. And then the fourth point is very, very specific to India actually. Collaborative work is it is of utmost importance, and it has become more important nowadays in this complex world. Collaboration is very important among people, among those working in a field, or among scientists, among students, because collaborative work leads to developments very fast. And this is something that is missing actually in our country. I have seen scientists working in the same department, same laboratory. If there are 5 persons working, they are working in 5 different rooms. They will all buy same equipment, but they will not collaborate and they will not let others share it. This is one of the drawbacks of our nature. You can see the example of this tenacity to walk the path alone in the greatest American inventor, Thomas Alva Edison. Thomas Alva Edison never had any formal education. He never passed any school education. Surprisingly, mother of Edison was a school teacher. So she used to teach him at home only because he didn't like to go to school. So she will teach him at school, at home only. And then this man will test any idea that comes to his mind. For example, he tested hundreds of materials before he hit upon the right material for the filament of his bulb. He is known for this discovery of this invention of electric bulb. Like this, he made hundreds of inventions then. In US, there are more than 1,000 patents in the name of this single person. So you must take, inspiration from the life of such persons. There is another famous person for the modern times whom the students are more familiar with, Steve Jobs, who was the co-founder of Apple, which is one of the most valuable companies in the world nowadays. He proclaims that because there are thousands and thousands of Indians working in his company, Apple. So he proclaims that Indians study hard, they will get an MBA, maybe they will buy Mercedes, but they lack creativity. So this is a question to you, whether you agree with this or not. And if you agree or do not agree, you can raise your questions about it later on, your arguments. Now I will come to the main theme of our talk, that is the time. Time is, when you measure the time intervals, basically what you need is something that, um, repeats itself again and again and repeats itself very precisely in the same manner so that you can use that repetition to define a time interval and make it your standard unit of time. Now, in nature, there are so many things which are in periodic motion. Hmm. And one of the most periodic motion is the rotational motion. And this world universe is full of rotational motion everywhere. In fact, the whole universe rests or kind of is controlled by rotational motion. So rotational motion is inbuilt into the nature. How? You can see that planets rotate on their own axis, and these planetary systems, they rotate around the sun or their own stars, wherever these planets are. And by now we know that there are thousands and millions of planetary systems in this universe, not just the solar system. Then the solar system itself is rotating in the galaxy, and this galaxy itself is rotating. Then, if you go to the microscopic domain, then you can see that electrons in the atoms rotate, then nucleons in the nucleus rotate. So it is fundamental to our existence. Our existence is because of the rotational motion. So this repetition of motion gives the first idea of time measurement. In fact, the first SI unit of time, which we call 1 second, was based on the rotation of Earth on its axis and adopted in 1960, which is not very old, only 60 years old. So this was the first unit that was adopted, 1 second. This was followed by the ephemeris second, based on the rotation of Earth around the sun. The way Earth is rotating around the sun, that time taken. So this was adopted 1967. Now, even before this, many kind of clocks have been used in history, based on flow of water or sand clocks, water clocks, so many kind based on some kind of spring motion. So they have been used in history, but most of them had large inaccuracies, very large inaccuracies. So they required daily adjustment. Every day the clock had to be adjusted. So here we should define what a clock is. By clock, we understand any device that can give an absolute time interval measurement. Any device. It doesn't simply mean that something, it has a dial, there is a hand going around and so on. So the meaning of clock is not, modern clock is not this. The digital clock don't have any hands. So recognizing this, first pendulum clock was devised by Huygens in 1657, almost 400 years ago. And it was based on harmonic motion of a pendulum, known as the second pendulum. So the pendulum goes around. Early pendulum clocks had an accuracy of 1 minute per day. That means every day it will go wrong by 1 minute. And this was later on improved to 15 seconds per day. So the clock became accurate by up to 15 seconds per day. And these continued to be used for many centuries and remained the main time measurement devices with improved accuracy. Slowly, they kept on improving more and more as they learned about the pendulum, the frictional force, and so on. Mm. Eventually, this was replaced by quartz clocks, which used the piezoelectric effect to create oscillations in a quartz crystal. And the initial accuracy of only 1 second in 4 months was reached. And this was improved to 1 second in 32 years very soon. And this was a remarkable achievement in those days. So the quartz clocks became accurate to 1 second in 32 years. This amounts to an accuracy of 10 to the power minus 9. And because of this accuracy, there were many new discoveries. For example, scientists discovered that there is a variation in the rotation of Earth. It's not fixed. It's not constant. So there is a variation. And then came slowly the atomic clocks. Rabi, you know Rabi, very famous scientist, in 1935, he used the magnetic interaction of nuclei with atomic electrons for time measurement. So the magnetic interaction of nuclei with atomic electrons, this led to this phenomena of nuclear magnetic resonance. You know, this nuclear magnetic resonance is the origin of the MRI images that you nowadays are taken routinely in hospitals, magnetic resonance imaging technique, where what is done basically is a proton, which is the nucleus of an hydrogen atom, which is a spin half particle. So when put in a magnetic field, the spin half proton can have two states, up spin and down spin. In the magnetic field, it can flip between these two spin up and down states. And this energy is very precise. And this flipping is what is known as the nuclear magnetic resonance. And this is used for the time measurement. This was used for the time measurement for the first time in 1949 at National Bureau of Standards in US, and the first atomic clock was developed. In 1955, Edison and Parry achieved an accuracy of 10 to the power minus 9 in atomic clock at National Physical Laboratory in UK. This is the same accuracy that one had for the quartz clock. So this was not a very big, people would say it is not a big development. But very soon, this accuracy kept on improving and it reached to 10 to the power minus 13 by 1960. That means in 300,000 years, this clock will go wrong, will have an inaccuracy, uncertainty of only 1 second in 300,000 years. So this was the accuracy of this atomic clock based on this NMR. Then, because of this, in 1967, the second unit of second was redefined, and it was defined as the time interval for so many cycles. You can read it, some 9 billion cycles of microwave stabilized to the hyperfine splitting in 133 cesium electronic level. This is the atomic clock. So accuracy of cesium clocks was further improved and technique of laser cooling was used. By that time, laser cooling had come in. So this was used to develop cesium fountain clocks by 1990s. And these cesium fountain clocks were incredibly accurate. They achieved an accuracy of 10 to the power minus 16 by 2005. 2005 is not very further from now, only 17 years ago. You achieved an accuracy of 10 to the power minus 16 by using the cesium fountain clocks. Then the optical frequencies were measured by using frequency divider chains. In all these clocks, you need to measure the optical frequencies on the light emitted by the atoms. So a major leap was taken with the development of frequency comb in 1998. This frequency comb was developed to measure the frequency very precisely, frequency of light. So the frequency comb, as the name itself suggests, no, it's like a comb which keeps combing the frequencies and gives you the exact measurement as precisely as possible of the time interval between two pulses in the light wave that is coming out. So these optical frequencies were directly counted actually by directly counting the oscillations in the visible light. So this was a huge improvement over the microwave range of electromagnetic waves used until then for counting. Until then, microwave range of electromagnetic waves were used, but now optical light became the standard. So counting of laser light oscillations led to optical atomic clocks with an accuracy of 10 to the power minus 17, sometimes 10 to the power minus 18. That is, they have an accuracy of 1 second in 30 billion years. For 30 billion years, the clock will not go wrong by 1 second. And you should know that the age of the universe is only around 15 billion years. This is the present estimate. Now, one would say, oh, this is more than enough. Why we are after all these things? These clocks implied a very fast and very accurate distance measurements, location measurements, speed measurements. All these things became very, very precise. The global positioning system, which runs the modern technology, everybody uses it nowadays, is based on such accurate clocks. The time signals coming from such clocks, if these signals are not there, they will fail. They utilize an array of satellites to find the right path. So when you use a map, online map, say Google Map or something, another map like that, then you immediately are using the GPS system, which is taking its time signal from somewhere and giving you a very precise location of every place. Presently, the location can be pinpointed to the extent of few meters accuracy. It also enables a plane, when you fly on an aeroplane, the pilot puts it on autopilot and moves around. He is not bothered about the flying of the plane. It looks scary, but it is very accurate and very, very robust system. Without any significant error in its path, the plane goes to the place where it is intended to go. Because when a plane is flying, whether it is national flight or international flight, It's a very complex pathfinding, and it has to go along a certain predefined trajectory. So the atomic clocks enable it to do that very precisely. Because of this, the second, the way 1 second is defined, it is it is very soon it will be redefined in maybe a couple of years. This is a schematic diagram of an optical clock. This picture is taken from this paper, and you can see that there is a laser source. This is my atom, which is acting as the standard of the light wave that is being emitted from it because of resonance. And this is a feedback loop which locks the laser to the frequency of the light that is being emitted by the atom. And this locked frequency is then counted by this comb here. And this gives you the time interval. So you define in 1 second so many pulses, so many oscillations of light must have taken place. That is 1 second. Now we come to the future clock. What the clock will be in the future? It may make a transition from an atomic clock to a nuclear clock in next 1 decade maybe. Why nuclear clock? Well, a nuclear clock, what is the difference between them? A nuclear clock will use nuclear transitions. That means just like in atom, you have atomic transitions and light is emitted when atom falls from one level to another level. In nuclear clock, then the whole nucleus will fall from a high excited state to a lower energy state, and a gamma ray or a light ray will be emitted. So that is going to be the standard. Why nucleus? Nucleus is very, very small, much smaller than atom. Therefore, it cannot be disturbed easily by electric and magnetic waves. Very difficult to disturb it. And it is completely aloof from the environmental disturbances, temperature and other things. So, these are the advantages, but there are disadvantages. For example, nuclear transition energies are very large. Hundreds of keV to 1 MeV. Does any student know what is the typical atomic transition energy? How much it is? They are in electron volts or at the most sometimes in keV, 10 electron volt, hundreds of electron volts like this. So because the nuclear transition energies are very large, you know this very nice relation E equal to h nu, and you can calculate the frequency. So the frequencies are going to be very, very large, and they cannot be manipulated externally. There is no way to manipulate them. And this is the reason that has prevented the development of a nuclear laser so far. But there is an opening here. The opening comes in the form of an isomeric state in 229 thorium. 229 thorium has an isomeric state which has been under experimental investigation for the last 50 years. Continuously, scientists have been doing measurements. I recently traced the history of this scientific development right from 1971. That was when the first mention of this isomer was made in a letter by Erskine to the Nuclear Data Center at the Brookhaven National Laboratory. The Nuclear Data Center was not at the Brookhaven National Laboratory in those days. It was, I think, at the Oak Ridge National Lab. And when the possibility of an isomer in 229 thorium was proposed by Erskine, he wrote a letter, and that's it. Then, since then, a large number of studies have been done. I will not go into all these things. This will require a whole talk in itself. Only recently, the lowest energy nuclear isomer has been found in 229 thorium. And you know what is the excitation energy of this isomer in nucleus? 8.12 electron volt. Nobody believed it. The nucleus could have such a low line level at 8 electron volt of energy. And this is now manipulation. One can manipulate, one can work with it, this kind of level. It can be externally manipulated. So this measurement itself involves a huge of a number of technological developments. I mean, the people who have measured this energy, see, just imagine it took 50 years to measure this energy, to establish that there is a level at 8.12 electron volts from the ground state. And they have used all kind of technology in it now, including handling of single ions, high vacuum, laser cooling, and so on, so forth. So many types of technologies have gone into it. This is a typical picture of 229 thorium. And you can see that the level at upper level is the isomeric state, and the lower level is the ground state. And these numbers, don't worry about them. Sukhjit can probably tell you if you want to know about it. These are Nelson quantum numbers. And it has an energy of 8.12 electron volt plus minus 0.11 electron volt. The corresponding frequency or wavelength, this is the wavelength. If you convert it into wavelength, Sc over lambda. So this wavelength is 152.7 nanometer, which lies in the vacuum ultraviolet region. So it's not exactly optical, it's in the ultraviolet range. And the lifetimes of this level and other properties like magnetic moment, quadrupole moments have also been measured. So this 229 thorium isomer, a precise knowledge of its excitation energy implies a stable and precise nuclear clock may become possible in near future. Hello? Yes?
Yes, please continue, sir. Please continue.
Okay, I am just about to finish it.
Okay, sir.
In near future, it is now expected to lead to a nuclear clock with an accuracy of 1 second in 300 billion years. So presently used atomic clocks have an accuracy of 1 second in 30 billion years. So it will be about 10 to 100 times more accurate. And if this is achieved, and scientists are very hopeful actually, they almost proclaim that we will reach that goal very soon. There are several labs around the world which are working on it. If this is achieved, then A precise knowledge of the excitation energy leading to ultra precise clock can make satellite-based navigation more precise. Your GPS will become more precise. तो कभी-कभी गलत गली में मुड़ जाते हैं GPS लेके, वो नहीं होगा. अब आप सही गली में मुड़ेंगे. But much better than that, 1 centimeter change in Earth's crust becomes measurable. If there is a change in the movement in the crust of the Earth of about 1 centimeter, that could be measured. What does it mean? It has very important consequences. For example, small strains in the crust can be measured, crust of the Earth, and these can be used in predicting earthquakes. Right now, we have no experimental technique which can predict earthquakes in advance. Although changes in the Earth's crust begin to happen weeks in advance. So such a technology will enable you to make such predictions then. Then one can measure things like the gravitational field very, very precisely, and how it causes the time dilation. It becomes observable, an effect of general relativity, which I mentioned in the beginning itself. This may lead to a whole new field like chronometric geodesy. This will emerge for research and development. Then the changes in gravity due to earth tides, because when tides come, there are changes in the gravitational field of the earth. The gravity changes. Seismic activity can be measured. Local weather becomes measurable. So because these clocks act as gravity sensors. So they can do all these things. So these are only a few of the advantages or the benefits that can accrue by the new kind of these nuclear clocks that are in the labs right now, but they may become available to mankind maybe in next 10 years. This is my guess. And with this, I close my talk and thank you all for listening to me.
Thank you very much, sir. There are certain questions from the students.
Yes.
And one UG final year student, she wants to ask something from you.
Good afternoon, sir.
Yes,
Sir,
good afternoon.
Time for us is what clock reads. So how do we determine that there is some inaccuracy in the clock itself?
Oh, see, very nice question. The inaccuracy, any measurement involves inaccuracies. Uncertainties are there in every measurement. And what are the inputs that are going into that measurement? Those inputs have some uncertainties in themselves. So using those uncertainties and the experimental methods, the final inaccuracy is determined. This in itself is a whole, complete field in itself. There are people who just do measure or determine the inaccuracies, uncertainties in a measurement. So this is not a very simple job. It's a complex thing, but it is done very, very meticulously. Okay, what is the accuracy of your measurement? Anything that you measure, for example, in the lab itself, you must have been taught the error analysis in labs probably. So it is similar to that, error analysis.
So I had one more question. You also
Yes.
mentioned that we should be reading literature. So literature is basically what shapes our mind towards certain direction of thinking. So basically, should be focusing on reading on books of our subject only, or more than that, uh, going outside or far field.
Anything that you like. I used to read lots of novels also, hundreds of them, from Hindi, from English, Urdu, all kinds of novels, poems, everything, not just the scientific books. I was very fond of reading stories and novels. So, of course, I used to read scientific books and the books related to the courses also. But it was my hobby to read lots and lots of things. So, the things that attract you, that charm you, you should read them.
Okay, thank you, sir.
Good afternoon, sir.
Yes.
Sir, my question is there any chance to prepare nuclear lasers?
Oh, yes. These developments are very much related to and point to the uh, possibility of having a nuclear laser in future. First of all, they are going to test the possibility of lasing action in this low energy isomer because it is doable. And once they have done it, then they will search for another situation. Actually, see, the difficulty is that you cannot change the levels of the nucleus. They are there. Nature has given us. It has given us hundreds of nuclei, and their energy levels are all predefined, fixed. We can only measure them. But you need a specific case or nucleus which is suitable for lasing action with the present technology. So that search is going on. But and thorium-229 fits into that actually to a great extent.
Okay, sir. And my second question is how atomic clocks, fountain clocks work, sir?
These are very, what is specialized things. I myself don't know much detail about it actually. And if you ask me the technical details of these clocks, I really don't know the technical details. They are very, very specialized technological developments. But you will find a lot of, articles on these things.
Okay, sir.
So
And my last
basically,
question.
yeah.
And my last question is, what is your views on space-time starting, sir?
On?
Space-time starting, sir.
No, I didn't get it. Space?
Space-time starting, sir. Space and time, sir. What is space and time starting?
Well, space and time, you see, this is a very delicate subject, and the work, the the work of Einstein in his general relativity was focused on this only, to put together space and time together on the same footing. But if you notice, when you go to the equations of Einstein general theory, then you will find that when he combines the space and time, then an imaginary term has to be brought in front of time. So, for example, the space-time distance between two events is given by x square plus y square plus z square plus ICT square, something like that. So that iota that comes in imaginary term attaches itself to the time. And this is very interesting because then time in quantum mechanics is not an unitary operator. All physical observables, they have operators which are unitary operators. But time is one observable, whose operator is anti-unitary in nature. And this makes it very mysterious also, and very difficult to tackle it. People have not been yet able to mm, uh, ex- tell why space is quantized, but time is not quantized. And they still don't know if time is quantized or not. And that is why the quantum theory has not been able to be applied directly to such mm, mm, situations where space-time can be put on the same footing. So there are many issues here involved. No, it's a very complex subject.
Okay, sir. Thank you so much.
Sir, since your talk is live on YouTube and there are three questions in the chat box.
Okay.
And first one is related to your talk directly. That is 229 thorium is the only case where state of electron volt excitation energies are observed.
Is the only case where
States of low excitation energy of the order of electron volt is observed. Yes.
it is the only case where the energy is in electron volts. There are 2 or 3 other examples of isomeric states where excitation energy of the order of 1 keV or 2 keV, which is also very low for a nucleus. But in electron volt, this is the only case. And people are still hoping that they may find another case also.
Okay.
But so far, first of all, to find such a case is very difficult, and measurement of such a case is very difficult. Doing such low energy measurements in nuclei is an extremely tough job.
And two general questions. First one is somewhat, it is not a question, it is your advice or suggestion for young students sitting here. First one is how to become a good nuclear scientist.
How to become a good
nuclear scientist?
You have to study hard nuclear physics. It's a tough subject. And you can go to a good school or a college where nuclear physics is, taught in a nice way. Not many such institutes are there, universities, where nuclear physics is practiced very well. So you have to find one such place and study hard. That is the only way.
And then second is students are seeking your advice while they are doing their UG and PG dissertations.
While they are doing?
While they are completing their such assignments or such projects or dissertations. How they can do some useful things while completing their UG or PG degree.
Yeah.
They are seeking your advice for the same.
No. What advice? What kind of advice? You mean some, until you ask me some specific question.
Yes, I think they are asking, suppose they are doing some their UG or PG project work, then what things should be taken care while they are doing some exercise?
One thing that I always tell students to focus upon when doing any project is to look for something novel, new. There should be some novelty in your project, some unique thing. However small it may be, but there has to be something unique, something novelty. Some novelty should be there. The novelty could be in many ways. Maybe a new way to calculate something, or you measure something and you find some new observation, or even your presentation of a particular topic or subject or some concept you try to illustrate or explain in a unique way. So that is something that one should try. And that makes your project valuable.
There is one more question, sir. I think this is the last question from the student. Yes, please.
Yes. What is the last question?
Hello, sir. My question is
Yes.
that you were previously talking about measuring time accurately, like supposing 99.9% we are measuring time accurately. So what will or how will it benefit us in astrophysics or cosmology, like predicting something coming in future or from Big Bang to anything like that?
Your voice was very low actually. So I'm not able to make out your words clearly. Mhm. If somebody can
Sir, my
consider
question
it.
is that you were previously talking about measuring time accurately. Sir, if we suppose if we are measuring time accurately to 99.9%, sir, how will it benefit us in astrophysics or cosmology, like from predicting something upcoming event in future or from Big Bang to anything like that?
Yeah. One of the expectations from such precise time measurements is that people may be able to find out if the fundamental constants that we use every day, do they change with time or not? Hmm. Are they changing with time? This has not been possible so far. So this will be a big leap actually, if you can tell whether Planck's constant is changing with time or the speed of light, is it changing with time? Mm. Even if the change is very, very small. So that will result in completely, new physics. So this is one of the expectations, and this will have a lot of impact on astrophysics and cosmology.
Okay, thank you, sir.
Yeah.
So I think there are no any question. Now I request Dr. Bir Bikram Singh, Head Department of Physics, to thank Professor Jain, please.
Thank you.
Uh, Thank you, sir. Thank you very much. So we are privileged to have you among us for this first International Student Symposium on Basic Sciences. And we are highly grateful and thankful that you applauded this unique initiative by the university and the organizers, and you congratulated for the same. And we are highly grateful for motivating our students for having good reading habits as per their own tastes and interests. Definitely, these habits will boost their scientific explorations in coming times. And definitely, your ideas that how time was explored or how it could become meeting ground for science and technological advancements. So I was reminding myself that how laser was first proposed this on the basis of theory of radiations by Einstein in 1917, and it took almost more than 50 years to have laser in actual practice. So similarly, you explored very well that how this 229 thorium isomer, this low-lying excited state, was explored in almost 50 years. So definitely, it could become possible due to several these technological advancements. And there was another discovery almost 10 years back of Higgs boson. It was elusive for almost more than 50 years after prediction of Peter Higgs in 1962. And definitely these science and technological advancements make, significant contributions in different type of explorations. And you beautifully explained on the basis of this time, how time measurement was made possible in last almost 4 centuries, that how accuracy has now become possible up to 10 to the power minus 13 second or 10 to the power minus 17 second in 30 billion years. And now we are hoping for this much accuracy to extend further its limits to another realms. So we are highly grateful, sir. It was highly mesmerizing to have this wonderful experience to explore this journey of time under the garb of this technological and scientific advancements over a period of time. So But sir, there are certain emotional moments which are attached to our lives, particularly Dr. Sukhjeet and myself. And when we met you almost, particularly myself, I met you 20 years back during SCRC school at Punjab University, Chandigarh. And I had just my master's from that department. And this school was actually turning point in my life to have my career in the field of research and academics. So I am highly grateful for that, sir. So it's a highly relevant platform to sharing this viewpoint. And let me tell you, students, that Professor A.K. Jain has nurtured nuclear physics in India. In coming times, definitely it would be memorable to cherish his contributions. And sir, we used to talk about why nuclear physics is lagging behind in India. And Professor Jain actually worked in his own department, and he raised the department like anything. And my so many colleagues or so many friends, they got placed at IIT Roorkee, and I can count those numbers. And it was only due to your efforts. And I think IIT Roorkee is the only place in India where nuclear physics department is flourishing, or nuclear physics is flourishing because of your efforts. And in other universities and other research institutions, still activities are going on, but your efforts are, very, effective and very, motivating for all of us. And how you are still motivating us by your scientific explorations, and your Facebook posts are highly motivating for all of us, particularly in recent times. Your book and your works in the area of isomers, they are highly motivating for all of us, sir. So during this talk, I was traveling all those moments in last 2 decades which we spent with you on and off. So I am highly grateful through this platform. I highly there are no words to express our thanks to your contributions and to your motivation to all of us. And your work will motivate coming generations as well. As we are in this roof, under this roof, we have more than 50 students. In coming times, they will make their mark in different areas of research. So thank you once again. And I am highly grateful to Dr. Sukhjeet Singh Dhinsa for his efforts, for pushing around us, for diverse research activities in the department. And hopefully this first International Student Symposium on Basic Sciences will be, a new leaf or a chapter in the history of this Kal University, and in India itself, because it is one of the unique, because it was also mentioned by Professor Banik in his inaugural talk today morning, that he has attended more than 500 scientific events like that, but he has not, he has not come across an event like this. So we are highly grateful, sir. So we applaud your efforts, and Professor Banerjee, he's among us. So thank you, sir. Thank you very much.
you.
So would love
Thank
to
you so
host you
much.
here, sir, in person. So you were
Yes.
mentioning that this is very difficult to have interaction online, but actually we were listening you very keenly. Your every single word was heard and listened by all the students very well and received very well. And we would love to host very soon, sir, here in this university, as per your availability and convenience, perhaps during next semester. So aana chahiye sir nu ki nahi bete? So it's a request from all of us, sir. For
Thank you. Thank you.
thank you,
I
sir. Thank you
will
very much.
definitely be there and meet you in person, Vikram.
Thank you, sir. Thank you very much, sir.
It's always a pleasure to meet you people.
Thank you, sir. Thank you very much.